So last time we started talking about like RLC circuits. We said if we have like two storage elements, we're going to get a second order differential equation. And assuming we have constant sources, we end up like getting like a second order differential equation with a constant force. And then we talked about like the solution of this second order differential equation. So to remind you of what we ended up getting, so we ended up getting a differential equation that looked like this: plus 2c omega naught dx dt plus omega naught squared xt equals some f of t. We said this c is the damping ratio, which told us exactly like what kind of solution we have, depending on if it was greater than 1 or less than 1. We knew exactly like what kind of solution we have. And then we said like this omega naught is undamped natural frequency, which was telling us if we have like sinusoidal solution, how fast this solution oscillates, right? We said the solution for this differential equation, so the solution for this differential equation is x of t, which has two parts: the particular solution plus the complementary solution. And we said the particular solution is due to the f of t, and the complementary solution was due to the homogeneous differential equation, right? We made the assumption that if f of t is constant, xp of t must be constant. So the assumption was f of t is constant, right? Which basically meant if I look at my circuit, all the sources that I have, they're all constant sources. So assumption, f of t is constant, which again means all sources in the circuit is constant. Therefore, we know xp of t must also be constant, and we call that a k. And we said like xc is the solution to this differential equation. ds squared dx dt squared plus 2c omega naught dx dt plus omega naught squared xt equals 0. Right? And we said we can look at the c over here, and the c tells us exactly like what type of solution we have. We also said to be able to solve this differential equation, we need to know the characteristic function. So the characteristic function here is s squared plus 2c omega naught s plus omega naught squared. That is 0. And this equation, that's a quadratic equation that produces two answers, S1 and S2. And given this S1 and S2, we know exactly like what kind of solution we have, which we already know by looking at that C, right? So let me quickly write that category. So types of solution, xc of t. The first type is when absolute value of c is greater than 1. which means S1 and S2 are both real. The solution xc of t is some constant k1 e to the s1t plus k2 e to the s2t. Right? And we call this solution overdamped. Right? The second type was when absolute value of c was 1, which we knew we had repetitive solution for the characteristic function. So let's call that S1 equals S2 equals S. And obviously, this is real. And we know the solution xc of t is some k1 e to the st plus k2 t times e to the st. And we talked about it. We said we have to multiply the second solution by t. So we have two independent solutions for this differential equation. So when we're computing the de Rhonskian, that is actually non-zero. Right? And we call this solution critically damped solution. And the last type was when the absolute value of c is less than 1, which we said S1 and S2 are both complex numbers. And we said if we write S1 as negative sigma plus I omega d, S2 must be the complex conjugate of S1. Therefore, it is negative sigma minus I omega d. Right? And we said the solution, xc of t, is e to the power of minus sigma t times k1 cosine omega dt plus k2 sine omega dt. And we call this solution underdamped. Right? And then we said, given the initial conditions that we have, whether it's a circuit or any differential equation, we can find k1 and k2. Right? So x of t, which is the whole solution, would be k plus xc of t. Right? So to have a unique solution for this differential equation, I need to find 3 variables. I need to find k, I need to find k1, and I need to find k2. Obviously, finding k is very, very simple, right? Because if you look at any of these equations that I have here, regardless of c greater than 1, equal 1, or less than 1, if I find the limit of x of t when t goes to infinity, right, the complementary solution actually approaches 0. Right? For example, for the first one, I know the value of S1 and S2 must be negative. And it comes from the fact that the circuit that I have is stable. So whenever you're computing your characteristic function, whenever you're computing the roots, the real part of the roots must always be negative. Keep that in mind. And it comes from the stability. If you're taking signals and systems or control classes, you're going to see to have a system stable, the real part of the solution must be negative. Right? So I know S1 and S2, both of them are real, so the real part is exactly the same. So S1 and S2 must be negative. So my x complementary, if t goes to infinity, approaches 0 for the first case. For the second case, Again, the first term goes to 0. The second term, I have a t multiplied by e to the st. But remember, the growth of t, the growth of a linear function, is much, much less than an exponential. So the exponential term dominates. So the whole thing actually goes to 0. So xc, again, goes to 0. And in this case, this is a sine wave. So it's always like bounded between like -1 and 1. So this e to the power of negative sigma t, that actually like dominates the whole thing and it approaches 0. Right? So in all three cases, if I find the limit of xt when t goes to infinity, I get k. So it comes down to the fact that I got to find k1 and k2. And it's basically due to the initial conditions that I have. And since I have two unknowns, I need to have like two initial conditions. Probably the value of x at some time, like t naught, and the derivative of this x at some time t naught. If I have like these two initial conditions, I can always find k1 and k2. Right? So let me quickly write that down. To find k, limit of x of t when t goes to infinity is always k in all three cases. To find k1 and k2, we need two initial conditions. So we basically need x at time 0, t naught, and, for example, dx dt evaluated at time t naught. Right? For us, most of the cases, this t naught is 0 plus. So for example, in circuits, t naught is often 0 plus. And this x can be anything, right? It can be some current, it can be some voltage, it can be anything. So let's just say, for example, it is current. So I need to know current at time 0 plus. And I need to know di dt evaluated at 0 plus. Right? If I assume x is it. But keep that in mind. This I might not be current through the inductor, so it might not be continuous. So we got to be able to find these initial conditions somehow. And as soon as I know these initial conditions, I can find k1, k2, and obviously k. Right? We're going to get into like details of it a little more when we're actually solving the circuit. But before we go through that recipe, let's just do like a few examples, just looking at the differential equation and see like how it works. Okay? Example. Let's just say I am given this differential equation. 8 dx dt plus 16 xt equals 0. Now let's just say I want to find natural frequency, I want to find damping ratio, I want to find the solution, I want to find everything. Right? First of all, if I look at the circuit, I'm not quite happy with it. Why is that? Why am I not happy with this differential equation? Because if I look at the leading factor here, it is not 1. So I'll make it 1. How do I do this? I'll divide everything by 4. If I divide everything by 4, I have second derivative plus 8 divided by 4, it's 2, plus 16 divided by 4, it's 4, and then 0 divided by 4, which is 0. Right? Now I'm happy. Now I can compare this to this differential equation that I have. And I know this coefficient over here is 2c omega naught, and this coefficient over here is omega naught squared. Right? I just need to compare it to this. What does this tell me? Omega naught squared equals 4. That tells me omega naught must be 2. Right? 2 times c omega naught equals 2 tells me I'm going to plug this in here. So I have 4 times c equals 2, which tells me c is half. Right? What do I know immediately by looking at this c? Exactly. What I do know is that like c is less than 1. Therefore, my solutions are sine and cosine, which means I have like underdamped solution, right? Since this less than 1, we expect S1 and S2, basically solutions of characteristic function, to be complex. And obviously, I am underdamped. Right? Again, we can use the formula that we had like last time to find S1 and S2. Right? S1 is negative c omega naught plus I omega d, and omega d was like omega naught times 1 square root of 1 minus c squared. Or we can just find the characteristic equation and solve the characteristic equation. I'll choose the latter because it's easier. So the characteristic equation here, the characteristic function, what is the characteristic function here? Well, it is s squared plus 2s plus 4 equals 0. Right? I know the general formula for this. Right? If I have as squared plus bs plus c equals 0, I know I have 2 solutions. And my solutions are minus b plus minus the square root of b squared minus 4ac divided by 2a. I can plug it in here. And I get my solutions S1 to be 1, negative 1, plus I square root of 3. I know S2 must be the conjugate of S1, which is minus 1 minus I square root of 3. Right? Again, remember this is my negative sigma, and this is my omega d. Right? So I know exactly like what my solution look like. Right? I know my solution x of t is e to the power of minus sigma t, which is minus t, because minus sigma is minus 1, times k1 cosine omega dt. Well, omega d is radical 3, so I have radical 3t plus k2 sine radical 3t. Right? And obviously, if I give you the initial conditions, you can find k1 and k2. Right? Given initial conditions, we can find k1 and k2. Right? Is that clear what's going on? Does that make sense? Let's do one more example. example. D squared dt squared plus 4 dx dt plus 4x equals 0. Again, let's just do like whatever we did in the previous example for this one. First of all, the leading coefficient is 1, so I'm good. I don't have to do anything. If I compare it to the equation that we had, we know this coefficient over here is 2c omega naught, and this is omega naught squared. Right? I know omega naught squared is 4, therefore omega naught is 2. I know 2c omega naught is 4. I plug this 2 in here, so I have 4 times c equals 4. Therefore, c over here is 1. Right? What do I know if c is 1? It is critically damped. And as soon as I know it's critically damped, what do I know about the solution of the characteristic function? I know the solution is real, and I have 2 solutions that are exactly the same. Right? So this is critically damped. Now I know I must have like one solution, right? I can find the characteristic equation. So the characteristic function is s squared plus 4 times s plus 4 equals 0. Right? But we know this is an identity. We know we can write this as s plus 2 to the power of 2 equals 0. Right? Remember that identity? Let me quickly give you a reminder. A plus b squared is a squared plus 2 times ab plus b squared. Right? You remember that? So I know this is basically s plus 2 squared. So I know s is negative 2. Again, as a sanity check, I can see the real part of s is negative. In this case, s is real, so it's negative. So I'm good. What is my solution? What is x of t? X of t is some constant k1 e to the power of minus 2t plus k2 e to the power of minus 2t. Am I correct? Am I correct? No, because if I look at this, I can combine k1 and k2 to like 1k, so I only have like one solution. But I know if I have like a second order, I have to have 2 solutions. So to make the solutions independent, I'm going to multiply the second term by some t. Right? Again, if I give you the initial conditions, I can find k1 and k2. Right? k1 and k2 can be found using initial conditions. Right? So that is very good. What I know is if I have any RLC circuit, and if I want anything in that RLC circuit, I have to write down a differential equation, and that differential equation turns out to be a second order differential equation. And assuming the sources I have in the circuit are constant sources, I know my particular solution is some constant, which I know exactly how to compute it. I just need to look at a circuit at time infinity, which I know at time infinity I'm in a steady state condition. So if I have a capacitor, I open it up. If I have an inductor, I short it out. Right? And all I have to do is to find a complementary solution. And to find a complementary solution, I write the characteristic equation for the differential equation that I found and decide on the cases. And I'm going to decide on the type of the complementary solution that I have, right? And again, remember, I need two initial conditions. So I have to use my continuity conditions that I had for a circuit, which means like VC at time 0 negative is the same as VC at time 0 positive. IL at time 0 negative is the same as IL at time 0 positive. I need to use these two conditions to find those initial conditions that I can actually solve the circuit with, right? So let me give you like a recipe as to how we can apply this differential equation to a second order circuit. So how to apply differential equation to a second order circuit. First step, we're going to make sure that all the sources we have in the circuit is constant sources. Okay? Step 1, make sure the circuit has only DC sources. Second step is to write down the differential equation that is representing the circuit. It does not have to be voltage across the capacitor. It does not have to be current through the inductor. It can be anything that's representing that circuit. So we write down the differential equation representing the circuit. And doing so, we're going to end up getting a second order differential equation, right? Because we have a capacitor and we have an inductor, right? So we end up getting a second order differential equation. We know the solution for a second order differential equation with constant force is some constant plus my complementary solution, right? So solution of this differential equation is xt equals some constant k plus x complementary of t, right? Now I have to find x complementary of t. To find x complementary, we're going to have to find the characteristic function. So we're going to write down the characteristic function, which we know is s squared plus 2c omega naught s plus omega naught squared equals 0. And then we find the roots. Given these roots, we know exactly like what type of solution we have. If they both are real, we got the case 1. If they're exactly the same, we have the case 2. And if they're complex, we have the case 3, which means like we have like a sinusoidal solution. So given these roots, we can determine the type of solution we have, right? Basically, if the C is greater than 1, my solution x of t would be k plus k1 e to the s1t plus k2 e to the s2t. If C is 1, my solution is k plus k1 e to the st plus K2 T e to the st. And if this C is less than 1, I know this x of t is K plus e to the power of minus sigma t, K1 cosine omega dt plus K2 sine omega dt. Right? All we got to do is to find K1, K1, and K2. Right? And we know this K, K1, and K2, they're imposed to us by a circuit. Right? So the next step is to find K1, K, and K2. As we just talked about, finding K is like very easy, right? Because in all three solutions that we have, if we find the limit of x of t, the complementary solution goes to 0, right? Because remember, like all the s's, the real part of them, they're negative. So they approach to 0. So to find K, we need to look at the circuit as t approaches infinity. And we know limit of xt when t goes to infinity is indeed this K. But what is happening at time infinity? We know we're in a steady state condition, right? So if we're in a steady state condition, what does it mean that we have a capacitor or an inductor? It's open circuit or short circuit. So note that at t approaching infinity, we're in the steady state condition. Which means if I have a capacitor, I have to open circuit it. If I have an inductor, I have to short circuit it. Right? To find K1 and K2, as we mentioned, we need two initial conditions. Let's just call them like x at time 0 plus and dx dt evaluated at time 0 plus. But remember, this x is not necessarily continuous, right? So we're going to go back to things that we know they're continuous. So we use continuity condition, which says if I have voltage across a capacitor at time 0 negative, it's the same as at time 0 plus. Current through an inductor at time 0 negative is the same as current through inductor at time 0 plus. And then we can find K1 and K2. If I do that, I know exactly like what my solution is. X of t is K plus K1 and K2 solution. And by this, I mean this is my X CFT, right? Whatever that is, right? So we're done. So let's do a quick example. I might not be able to finish it like today, but if I'm not able to do that, we're going to do it like next time. But let's get it started and see like how we can actually do this, right? Let's have a second order circuit and try to apply this method. So example. Let's just say I have this circuit, 2 ohms. I have an inductor 1/400 farad. I have a 1 Henry inductor in parallel with a 10 ohms resistance. And the question is like, what is this V out for all times greater than 0? And let's just say I have a switch that it is at position 1. And as soon as I hit time 0, it goes to position 2. Right? So basically for negative time, it is in this position, position 1. And as soon as I have like time 0, it goes to position 2. Right? What is the first step? We got to check if there is any source but DC source or not. Well, in this case, it is DC source, so we're good. Right? It's a constant source. So the second step would be to write down the differential equation that's representing this circuit for all times that are greater than 0. Right? So for time greater than 0, I know this switch is going to go to position 2. Right? So my circuit would look like this. One Henry and 10 ohms. Right? And the question is, what is this V out? Do you agree I can call current through this capacitor IC, current through this inductor IL, and current through this resistor IR? It's just a name, right? Do you agree I can write a KCL at this top node? I can do that. If I do that, what do I have? I have IC plus IL plus IR. That must be 0. Right? And this equation holds true for any time that is greater than 0. So if I give you any time at greater than 0, you can plug it in here, and this equation should satisfy. Right? This is by far the most important equation that you get when you're solving such a circuit. So this equation holds true for all times greater than 0. And since it's a very important equation for us, I'm going to call it equation 1. Okay? It's just a KCL. But we know it's true for any time that's greater than 0, including 0 plus. Right? Do you agree voltage across this resistor is exactly the same as voltage across this inductor, is the exact same as voltage across this capacitor? They are, because they're all in like parallel. And we know this voltage is like V out. So what is IC of t? I know voltage across it is V out. What is, and I know current through it is IC. What is the relationship? IC is C dV dt. So IC of t is C dV out dt plus. Do you agree voltage across this inductor is also at V? What is the relationship between I and V? It's that integral that we have, right? So this is plus IL at some time t naught plus 1 over L integral from t naught to t of V out tau d tau. Right? So far, you with me? What is IR? I know voltage across it is V out. What is current through it? It's Ohm's law, right? So it is plus V out T divided by R, and that must be 0. Now I'm in a little bit of a pickle. I have an equation that has both derivative and integral. I can't deal with it. The only way I can deal with it is to get rid of the integral. How do I get rid of the integral? I take derivative. So if I take derivative, C is constant. So I'm going to have the second derivative of V out. What is the derivative of IL evaluated at T naught? It's 0 because it's a constant, right? It's the value of I evaluated at one point. So it's a constant. So that is 0. 1 over L is a constant. What is the derivative of an integral? That's the integrand. That's basically like whatever that's inside the integral. What is it? That's V out evaluated at this T. So that's V out T. 1 over R dV out T dt. That must be 0. Right? Again, I have a differential equation that has a leading factor that's not 1. How do we get rid of it? We divide everything by that constant. In this case, we got to divide everything by C. So my differential equation becomes d squared V out dt squared plus 1 over RC dV out dt plus 1 over LC V out T. And that's 0. And this is true for all time greater than 0. Again, I have the value for R and C. R is 10. C is 1 over 400. L is 1. I can plug them in here. And if I do this, I'm going to end up getting d squared V naught dt squared plus 40 dV out dt plus 400 Vt equals 0. Right? I just plugged in the numbers. Right off the bat, if I look at this equation, since there is no f of t over here, I know my k must be 0. Right? We're going to drive it by looking at the circuit at time infinity, but this is as a sanity check. Since there is like nothing over here, my f of t is 0. So my constant, k, must be 0. Right? But we're going to drive it. But for now, look at this circuit. Look at this differential equation. I know this differential equation is representing the circuit. So I got to solve it. How do I solve it? We're going to look at the characteristic function. What is the characteristic function here? Again, I know the solution for this is sum k plus x complementary of t for all time greater than 0. To find x complementary, we need to look at the characteristic function, which is s squared plus 40 times s plus 400, and that must be 0. Right? Again, we have that identity that we just talked about. I can write this as s plus 20 to the power of 2 equals 0. Therefore, s is negative 20. Right? So what is my solution then? I know V out T must be that constant K plus some constant K1 e to the power of minus 20t plus k2 times t e to the power of minus 20t for all times greater than 0. Right? And my job is to find k, k1, and k2. Again, as I mentioned, we already know this k is 0 because the force function in the differential equation is 0. Right? But again, to be able to find it, we're going to have to look at a circuit at time infinity. Right? Since I'm running out of time, I'm going to stop here. And next lecture, we're going to find k, k1, and k2 by basically looking at the circuit. I'll see you guys Friday.